In the last video, we walked through a model in which the dynamics of the proportions of two cell types in a population depended on how often different cell types collided with each other. In this video, we describe a more traditional form of game theory so that we can eventually explain why the kind of modeling from the previous video is often referred to as evolutionary game theory. We wish to describe a business transaction between two people, one on the left and one on the right. We want to describe the payoff that each business person receives. To simplify our model, we assume that each business person can execute either of two business strategies labeled copper or denim. For example, let's say that the person at the left executes the copper strategy. In order to specify the payoff that each person receives, we have to specify the strategy of the person at the right. If the person at the right executes the strategy labeled copper, we use R to denote the payoffs that each person receives. If the person on the right executes instead the strategy labeled denim, we say that the copper individual receives payoff S and the denim individual receives payoff T. The same payoff parameter names are listed in reverse if instead the person on the left is denim and the person on the right is copper. Finally, if both individuals are denim, we say that each individual receives payoff P. This kind of information is usually presented as a table with rows corresponding to the strategy of one person and columns corresponding to the strategy of the other person. The icons in the middle of the table are usually omitted, leaving more room to write out the payoffs in a taller typeface. This table is usually called a payoff matrix. In this slide, we have two purposes. We want to show that each business person can use the payoff matrix to determine what strategy to perform in order to maximize his or her own payoff. We also want to illustrate a situation in which both individuals receive less than the maximum possible payoff, even though they both use this table to guide their strategy choice. Consider the collection of situations in which T is greater than R is greater than P is greater than S. Suppose that individuals try to adjust their business strategy to maximize the payoff they receive. Suppose you are the person on the left. You consider the possibility that the person on the right is copper. If you execute the copper strategy, you receive payoff R. If instead you are denim, you receive payoff T. Because we said that T is greater than R, you should maximize payoff, receiving T instead of R by adopting the denim strategy instead of the copper strategy. You are still the person on the left, but now you are considering the possibility that the person on the right is not copper, but instead denim. If you execute the copper strategy, you receive payoff S. If instead you are denim, you receive payoff P. Because we said that P is greater than S, you should maximize payoff receiving P instead of S by adopting the denim strategy instead of the copper strategy. Whether you consider the possibility that the other business person is copper, or instead the possibility that the other business person is denim, you always obtain a check mark for denim. Thus you adopt the denim strategy. In the same way, the person at the right will also adopt the denim strategy. As we said, T is greater than R. When the person at the left is copper, the person at the right maximizes his or her payoff by being denim and receiving T instead of R. As we said, P is greater than S. When the person at the left is denim, the person at the right maximizes his or her payoff by being denim and receiving P instead of S. Both of these check marks indicate that the person on the right should be denim. We say that denim versus denim is a stable strategy pair in the sense that neither business person can increase his or her payoff through unilateral strategy change. Suppose that you are again the person on the left. Can you improve your payoff by changing your strategy from denim to copper? No. You have already chosen the strategy that gives you the maximum payoff, given that the other business person is denim. If you now adopt the copper strategy, you will forfeit the higher payoff P and receive, as a lesser substitute, payoff S. The strategy pair denim versus denim is stable in the sense that neither individual would want to change strategy. We were guided to the strategy pair denim versus denim because T is greater than R and P is greater than S. In this situation, each individual receives less than maximum payoff, receiving P, which is less than T, because the other individual has also adopted the denim strategy. To illustrate this point, regard yourself as the person at the left. You would like it if the person at the right were copper, because this would give you a payoff of T, which is greater than the payoff of P you currently receive. Unfortunately for you, the person at the right is denim, so you receive payoff P, which is less than the greatest payoff T that could possibly be awarded to a person executing the denim strategy. Each individual receives less than maximum payoff, receiving P, which is less than T, because the other individual has also adopted the denim strategy. The language of strategies and payoffs and the conclusions that we have just briefly walked through are a cursory introduction to what is collectively referred to as game theory. We can now provide a sense of why mathematical models like the one from the previous video are sometimes referred to using the phrase evolutionary game theory. In the previous video, we studied a population dynamics model, and in this video we described a payoff matrix, which is used to study the outcomes of a business transaction. We will now summarize the two analyses side by side in order to show why they are sometimes described using common language. On the left, we considered a set of inequalities that stated that T is greater than R is greater than P is greater than S. We gave these parameters meaning, basically by regarding them as rate coefficients for cell replication events triggered by cell-cell collisions. After we wrote equations describing the dynamics of the system, we found a homogeneous steady state corresponding to PD equals 1, meaning a population composed purely of denim cells. As the population becomes increasingly enriched in denim cells, the fitness of both cell types decreases. On the right, we wrote the same set of inequalities stating that T is greater than R is greater than P is greater than S. Rather than writing down a model for the dynamics of a population, we considered the possible outcomes of a business transaction. We assumed that each business individual tried to adjust his or her strategy to maximize payoff. We concluded that each individual would adopt the denim strategy. If either one individual tried unilaterally to adopt instead the copper strategy, he or she would receive a lower payoff. Both individuals would want to stay on the denim strategy. In this sense, we regard the strategy pair denim versus denim as a solution to this analysis. Each person receives a payoff P that is less than the greatest payoff T that can be received by denim individuals because the other individual has also adopted the denim strategy. For historical reasons, the inequality T is greater than R is greater than P is greater than S is, on both sides, called a prisoner's dilemma. Looking up this phrase on Wikipedia will reveal not only why these parameters happen to be labeled T, R, P, and S, but also why the cell types and business strategies described here have been labeled using names that begin with the letters C and D, meaning the names copper and denim. On the left, we studied the dynamics of cells replicating according to fitnesses that depended on how often different cells collided with each other. On the right, we considered individuals trying to maximize payoff. We may regard this as a basic element of business sense or so-called rationality. On the left, we found an evolutionarily stable strategy. The denim cell type is stable in the sense that a population composed purely of denim cells will, over time, return toward the state of being composed purely of denim cells, even after being disturbed from that homogeneous composition by the momentary introduction of a contaminating subpopulation of copper cells. On the right, we saw an example of a strategy pair that is called a Nash equilibrium. Both the analysis on the left and the analysis on the right lead to conclusions that sound like profound philosophy. In both analyses, there is a notion of a cell type or business strategy that dominates. This has been labeled denim in both cases. There is also a notion of a cell type or business strategy not performing as well as it could. On the left, this corresponds to replicating more slowly than possible, and on the right, this corresponds to receiving a lower payoff than possible. Specifically, there is a notion that the fact that denim is dominant is detrimental to denim. At least at the level of sentiments and notions, the analyses lead to conclusions that are similar. The tabular analysis on the right is a basic introduction to a much broader body of work called game theory. The analysis on the left is an example of studying evolutionary dynamics that depend on how often cells collide with each other. T, R, P, and S have related roles in the two analyses. On the left, these parameters describe how replication rates are modulated by how often cells collide with each other. On the right, these parameters label payoffs that business people can receive during transactions, depending on which strategies they bring to the table. A connection is often drawn between the two analyses by regarding the cells in the test tube as miniature business people. The vigorous stirring of the contents of the test tube causes ongoing microscopic collisions, each of which constitutes a miniature business transaction. The miniature business people, meaning the cells, do not have the discipline to save their income long term. The payoffs that each miniature business person earns is spent quickly to modulate the likelihood of replicating in a short interval of time soon after the transaction. By carefully preparing the analysis on the left and the analysis on the right, we can contrive the stable, steady state of the analysis on the left to give us intuition we can use to guess the stable strategy pair of the analysis on the right. In this sense, we can say that the evolutionary dynamics model on the left provides insight into the related game theory model on the right. It is time-consuming to read the phrase, evolutionary dynamics providing insight into a related game theory model, so we refer to the analysis on the left simply by saying, evolutionary game theory. In this slide deck, we aimed to accomplish three purposes. Using the picture on the left, we introduced a class of models of the dynamics of populations in which the time rates for events that alter population numbers depend on how often various combinations of cells encounter each other. Using the tabular picture on the right, we described a basic example of a model from game theory. This allowed us to explain why the mathematical modeling described on the left is often referred to using the name evolutionary game theory.